Hello everyone. Today I will derive electric field due to uniformly charged thin spherical shell. So this is the spherical shell with radius capital R. Okay. So we are supposed to find the electric field at some point P, maybe here, from the center. Suppose this point from the center is at a distance of R. Okay. The radius of the given shell is capital R, but this distance is R. See, this distance is R. The radius of the shell is capital R. To be careful, radius is capital R, but the distance we have taken from center to P is R. So I am interested that due to this shell, what will be the field at this point? Okay. So we will use the definition of flux and Gauss's law to find the electric field at this point. Okay. So by definition, what is electric flux? The electric flux by definition is said to be the product of E, which is electric field intensity, and the surface area over which we are finding the flux. Okay. And this product is dot product. Dot product means cos theta. So this is what we use the basic definition for electric flux. Okay. Here we know that theta is nothing but 0 degree. Why? Because E is the electric field intensity. Okay. So the electric field intensity on this surface will be outward. Here electric field intensity. And if I want to know what is the surface area E vector. So E vector is always perpendicular to the surface. So this is del S. So we can see clearly the angle between E and S. So this is nothing but angle between E and del S. So this angle is 0 degree. Okay. And we know cos 0 is 1. So that's why we can say the flux is nothing but E del S. E is the electric field intensity and del S is the area. Okay. So if we want to know the total flux, the net flux will be nothing but sigma of E del S, okay, which is nothing but E sigma del S, E sigma del S. So what is sigma del S? Sigma del S is nothing but total area. Sigma del S means total area. Okay. Sigma, the meaning of sigma is entire area. So what is the entire area of this shell? So because this is a sphere. So sphere area is how much? Is nothing but 4 pi r square. Correct? Because I need to take the electric field at this point. So if at this point I assume there is a sphere. So what will be the area of this sphere? Will be nothing but 4 pi r square. Okay. Because we are supposed to find out the electric field at this point. So we will assume there is a sphere at this point of radius r. Correct. So this is the phi net. So this flux we got from basic definition. I hope you understood. Now we will find out flux. How much will be the flux due to Gauss's law? So what is Gauss's law? Anyone remembers? Gauss's law says that flux at any surface, flux means electric field lines coming out of any surface is nothing but Q by epsilon naught. This is Gauss's law. Correct. To find out to apply the Gauss's law at this point, we will consider imaginary sphere at this point, and this is called Gaussian surface, because we will apply the Gauss's law over this surface. So this is called Gaussian surface. So over this surface, how much is the net flux coming out is nothing but the charge enclosed divided by epsilon naught. Correct? Q is the charge enclosed. And what is epsilon naught? Epsilon naught is nothing but permittivity. Permittivity of the medium. This is the flux. So how much is the charge enclosed in this surface is nothing but the charge on the given shell, and that given charge given on the shell is Q. Okay. So net charge enclosed is nothing but Q. So this is the equation 2 by the Gauss's law. So the first equation is saying flux is this. Second equation is saying flux is Q by epsilon naught. So can we say that both flux are equal? Because one is by the basic definition and one is by the Gauss's law. So here we can say E into 4 pi r square is equal to Q by epsilon naught. And our purpose is to calculate E. So what will be E here? E is nothing but 1 upon, this will go here, 1 upon 4 pi r square Q by epsilon naught. Or we can arrange it 1 upon 4 pi epsilon naught Q by r square. So this is the net electric field at some distance r from the center. So this is the first formula. So E at any distance is nothing but 1 upon 4 pi epsilon naught Q by r square. Okay, at any point. Now we were interested if r is equal to r, means right at the surface, exactly at the surface, what will be the electric field? Right at the surface means here, somewhere here on the surface, here. How much will be the electric field? We are interested. So what should we do? Think about it. What should we do? Just we should put E is equal to 1 upon 4 pi epsilon naught Q, and what is R here? R is nothing but capital R. So this will be nothing but this. E is equal to Q by R square. Right? This, remember, this has to be capital R. Here it was a small r. Here it is capital R. Third case, we are interested. How much is the electric field inside the shell, at the center of the shell? Okay, here at the center. So for that, we need to apply the Gaussian surface somewhere inside. Suppose I am interested, there is some point inside shell. Okay, inside shell, and there may be some point, say this is the point T. Let me write down. This is point T at some random distance, maybe r dash. So if I assume there is a Gaussian surface inside of radius r dash, so what will be the electric field? 1 upon 4 pi epsilon naught Q by r dash square. Correct? But point to be noted, within this region, which is the inside Gaussian surface. Okay? So let me write down. So here, this is the inner Gaussian surface that we are assuming for inside. This is the Gaussian surface. So what is Q? Enclosed Q is nothing but 0, because all the charges outside the Gaussian surface, because the shell is outside. Okay, so inside, within this region, the net charge enclosed is 0. So if I put Q is equal to 0, if this is 0, so what will be the net electric field inside? Will be 0. So inside the shell, net electric field is 0. So these are the three formulas which will give us an idea about the electric field at different places from the shell. Now, let me draw a graph depending upon the distance from the shell. So this is E, electric field, and this is the distance, the variation from the center. At this point, suppose there is a center where R is 0. So as we move on from the center to the shell to the point where R is equal to capital R, which is equal to the radius of the shell. Okay. So Till this point, the electric field was nothing but 0. Because if we observe inside the shell, from here to here, the net charge was 0. Okay. But exactly at R, the electric field suddenly jumps. Okay. And what was the value of electric field here? It was 1 upon 4 pi epsilon naught Q by R square Newton Coulomb. Newton Coulomb is the unit. Always remember. Okay. So this much is the electric field. And after this, electric field kind of decreases. Why? Because the electric field formula was 1 upon 4 pi epsilon naught Q by R square. So clearly we can see as R will increase, because this is inversely proportional, R will increase, E will decrease. So this is the graph which is showing the pattern of changing electric field with distance R. So here we can see from center till the surface. This is the point at the surface, exactly at surface. Till here it is 0. At exactly at surface, it becomes very high electric field. And after that, as we move away from the shell, here, or here, or here, as we move on away, it will decrease with distance. So this was all about the electric field due to a uniform shell. See you next video. Bye everyone.